Hey everyone, I'm Dan, and today I'm going to talk to you about a Java developer's guide to supply chain security. So a bit about myself. I'm a software engineer over at Bloomberg. I am a guild leader in the Java and JVM guild, so this is beyond our normal day-to-day working responsibilities. What we do is we effectively are able to contribute to the community and grow Java infrastructure for teams all around Bloomberg. And beyond that, I'm also happy to participate in Adoptium in the Secure Dev working group. So today I'm going to talk to you about basically what you should know as a Java developer about supply chain security. If you've seen some of the other supply chain security talks in the past few days, this one's going to be a bit more basic. But if you've missed those, this is probably a great place to start. So what is supply chain security? Supply chain security is basically the idea that our software is secure not only itself, but also all the components that go into it. And today we're going to discuss what it is, why do we need to care about supply chain security, how does supply chain security apply to the Java and Java virtual machine ecosystem, and what tools we can use to secure our software systems. And if you've been at many different talks in this conference, you'll know that this is not, this talk is not comprehensive. There are plenty of tools out there. So take this as a starting point, not a comprehensive list. So supply chain security. Modern software is not made from scratch. I believe one of the previous talks mentioned something like 77% of released commercial software is open source by lines of code or something. So modern software is not made from scratch. We use libraries and frameworks to speed our development. And the thing is that by using libraries and frameworks, we get all the benefits of the functionality they provide, but we're also exposed to any risk that they may introduce, right? So if an attacker is able to compromise a library or a framework, they're not only compromising one project, they're compromising all the projects that are using that library or framework. And supply chain security is the practice of ensuring that our end products are not compromised by vulnerabilities, not only in our own code, but also in the code that we bring in through our dependencies. And it's worth mentioning that supply chain vulnerabilities can either be malicious or they can be intentional, right? You can have a supply chain vulnerability completely by accident, or you can have one because somebody has decided to try to exploit your software. So the concept of software supply chain security starts pretty early on. Some sources consider the 2000 Solar Designer exploit of the generic malloc to be a starting point, so we'll start there. Before this, most exploits targeted individual pieces of software. Solar Designer is a prolific security researcher, demonstrated that Doug Lee's malloc, which is a very widely used version of malloc, which was originated in 1987, could be exploited. So fun Java fact for the Java programmers in the room, hopefully most of you, is that Doug Lee is actually one of the originators of Java concurrency as well. The Wikipedia page is well worth a read. And he still contributes to the OpenJDK. His last PR was in 2023. So Doug Lee, beyond being one of the authors of a very widely used implementation of malloc, is also one of the kind of leading figures in the Java world. So that was in 2000. The supply chain attacks have really only grown since then. I'm sure everyone has heard of Log4Shell. It's a vulnerability that existed since 2013, reported to Apache in November 2021, made public in December 2021. So it basically, Log4j allowed arbitrary requests to LDAP and JNDI servers to be used, and they could be exploited to let attackers run arbitrary Java on a server, which, as you may know, is a really dangerous thing. So analyses by this Wiz EY study said that 93% of enterprise clients were affected. And the fix, as is the fix with most software supply chain vulnerabilities, is to upgrade, right? The open source community discovers a vulnerability, somebody goes in and patches it, you've got to upgrade. A common problem for us especially was finding all the places where the affected version of Log4j was deployed, right? So even if you know that a library is affected, the question is, what are all the places that you're using it? And that doesn't just mean what are the places that you have it in your POM XML or the great old dependencies list. It's all the places that you have a dependency that somewhere down the dependency tree has that affected version, right? So that was kind of a wake-up call to many people. So, fun fact, almost 3 years after the Log4Shell vulnerability was made public, 13% of all Log4j installations are still on the vulnerable version, right? So that's quite a lot of code, right? Considering that 93% of enterprise clients were exposed to the Log4Shell bug. The fact that 13% of the installations are still running the vulnerable version 3 years later is terrifying. And the number of malicious packages floating around open source communities that we know of is up 156% compared to the last year. So supply chain security is a really big deal. And of course, the obligatory XKCD comic. For those of you like myself based in London, the XKCD author is in London in November giving a book talk. So of course, his work, I'm sure everyone's seen this, but the thesis is that all modern infrastructure is based on or relies upon some project some random person in Nebraska has been thanklessly maintaining since 2003. XZlibs was effectively a prime example of this. So there was kind of one maintainer for a really long time, kind of originator of the project and maintainer. And the attacker embedded a backdoor allowing users with a certain SSH key to SSH into machines and basically do whatever they want. But the software had to be built on in a very specific way, I believe, on Red Hat or Debian. So basically, they embedded the attack in the test file, in a binary file which was being used for a test. And then it was decrypted into a .o, which is like a compiled C file, but only if the build was on Red Hat or Debian. And the scary, scary thing is that the attacker spent two and a bit years getting involved in the project and building credibility to take over ownership, right? So for those of us that work in open source and for us, trust is number one currency, right? The scary thing is that this attacker spent so long building up trust, gaining that currency. So that was absolutely terrifying. And then basically they put in this really, really, really difficult to detect attack, which was thwarted by a Microsoft employee who noticed that the SSH login had really, really slowed down and was able to profile it. But it was a really well-obscured attack, right? And this is kind of a great example of a malicious software supply chain attack, right? Basically, they were trying to get access to a very, very broad array of servers by embedding in this library that a lot of different systems use. So that's a very recent example. This came out this year. One that came out a few years ago, which was kind of also equally interesting, also equally malicious. If you're aware of Python, I know this is a Java talk, so sorry, we'll do a little bit of Python. If you, much like in Java, we install packages from Maven Central or some mirror of Maven Central. The popular package place in Python is PyPy. So the attacker was effectively able to hijack a project in pip because the project login was kind of tied to an email address, and the email address used for that project was in somebody's like personal domain. And the domain had expired, so the hijacker bought the domain, of course giving them access to that email address. And then they uploaded malicious versions of the CTX library to pip, and that malicious version, what it would do is it would take all the environment variables and their values and upload them to a remote web endpoint running on Heroku app, right? For those that don't know, Heroku is just a kind of a generic application hosting platform. So they were stealing all these environment variables. And of course, environment variables are where people tend to love to store their secrets, database passwords, things like this. So the attacker, by hijacking this library in pip, for a brief period of time, all the new downloads of CTX from pip were containing this malicious code, and that meant that the hijacker gained access to people's environment variables. So those attacks are really scary, and we don't want to subject ourselves to them. But there's another arm, especially if you're working in the software business. There's a ton of regulation And there have been actually some really, really good talks about CRA at this conference already. I believe one yesterday morning I went to was really, really good. And I think there's more. So highly recommend those. And these new regulations effectively are saying that software manufacturers have a duty of care to end consumers, right? So in the same way that if you go and you buy a bottle of juice at the store, you're kind of guaranteed by the manufacturer of that juice that it will not contain anything that will make you sick or kill you. In the same way, they believe that software manufacturers have a duty of care to consumers, that when you buy software from a manufacturer, it will not contain anything that will do you harm. So you must ensure that your software is secure by default. This includes securing the software against supply chain vulnerabilities. And it produced a major panic in the industry because people realized that we don't actually know all that much about what's in our software, or at least we didn't. So in America, there's a very similar regulatory motivation. They have the Secure Software Development Framework. This is a set of fundamental sound and secure software development practices. It's got 4 pillars. 1, prepare the organization. 2, protect the software. 3, produce well-secured software. And 4, respond to vulnerabilities. So as you can tell, these 2 regulatory frameworks effectively are saying the same thing. Make sure you're producing secure software. And as a result of them, we have to really understand what goes in our software and understand how we deploy our software, right? So this is mostly from my experience, but this is what a typical corporate Java supply chain could look like. So you've got the green stuff is kind of stuff that your organization might own, and the red stuff is stuff that your organization doesn't own, right? So let's say you're using a library, I don't know, Apache Kafka client or something like this. That's going to originate on external version control. In the case of like Apache Kafka client or Zookeeper or whatever, that would be on like GitHub, and then that would be built in some way that you don't control, and it goes to Maven Central. And then your company might have, that one is kind of between red and green, an internal mirror, right? Some companies might use something like an Artifactory to mirror Maven Central, and that gives you access to things like checksums to make sure that the versions of the packages aren't being changed around. But basically that's where like your external software is usually going to come from. It's going to be a lot of libraries and things like that that are coming from something like GitHub or GitLab, going through that library hosting service, and then will get ingested into your company. And then your code is usually on your company's version control, generally some kind of Git, unless you're one of these companies that has a big monorepo and a separate system. But anyway, so you've got the external code living outside, your code living inside. All this stuff gets pulled in to build machines, and this, depending on your company, this could be, if you're using like GitHub, you could be using GitHub Actions. If you're not, you might likely be using something like Jenkins. And this build orchestration would call into your build system, generally Maven or Gradle. And then you've got your JDK. Hopefully this is Eclipse Tamarin. If it's not Eclipse Tamarin, consider using Eclipse Tamarin. It's free, it's secure. There's a lot of great talks about it at this conference. So all of these things, all of these components could be compromised. And then once you've built your software, you've got some kind of deployment process, which will take the output, usually a jar, generally an Uber jar, and it'll somehow move it over to, probably through a couple deployment stages, eventually ended up in your production stage where you've got the jar, and you've also got the runtime environment, which again, could be Tamarin's GRE, or it could be something else, hopefully Tamarin again. But all of these steps could have compromise, right? You could have a compromised library pulling in. Unlikely, but somebody could be messing with Maven Central and putting a compromised version there. Your code could be compromised. Somebody might have made a rogue PR. Your internal company mirror could be compromised. The build machine could be compromised. The build orchestration could have some compromised steps in it, right? Theoretically, your build system could have some compromised code in it. The JDK might be compromised, and in production, your deployment process might actually insert some stuff in there that you didn't expect. The runtime environment could be compromised. The jar in production that was built and deployed could be compromised, and of course your production servers could be compromised. So there's a whole lot of places where you might have risk. So step back a bit. What is a software vulnerability? A software vulnerability is a flaw in a computer system that weakens the overall security of the device/system. So some common things you could do with an exploit, right? If you're exploiting vulnerability, you could make a system crash. You could corrupt some data. You can read some data which you're not supposed to read. You could hijack a computer and make it do whatever you want it to. Generally, if you have a vulnerability, common fixes are either to upgrade to a patched version of the thing that's vulnerable. If you own the code, obviously you have to patch it before you upgrade to the patched version. If it's somebody else's code, hopefully they've patched it for you. If it's open source, you can either collaborate on the patch or use somebody else's patch. And then the other fix is to stop depending on the vulnerable component. What you don't want to do, generally speaking, is to continue to rely on the vulnerable component if it's making you vulnerable, because that leaves you vulnerable. So 0 day, this is a term for an exploit that's immediately targetable. Basically, you've got 0 days to react to the vulnerability before it's exploitable. Couple super famous 0 days. We've had Stuxnet, Heartbleed, Shellshock, WannaCry, Sandworm, Log4Shell. I've actually read a really good book on Sandworm that's available. So these are fascinating reads. There are great articles about them. And as you can see, they have some real world implications, right? Iran's nuclear facilities were shut down. Ukraine had power disruptions. So these can cause effects way beyond the software sphere into the physical realm as well. And there's kind of this idea of a window of vulnerability. The software is basically vulnerable from the time that vulnerability is discovered by anyone. And hopefully it's not the hackers that have discovered it first, but it could be, until the time that a patch is released and all the software is upgraded, right? So basically, you're vulnerable from the point that the vulnerability is discovered to the point that you have patched your system, right? It doesn't really help. In fact, it's generally unhelpful if somebody else has discovered the vulnerability and it's known, but you haven't patched your system. So the moral of the story is, once a vulnerability is known, moving to get that patched version out and replacing the vulnerable version is very important. And over time, the proportion of patched systems tends to increase and the exploit becomes less and less potent. So the biggest opportunity for people exploiting vulnerabilities is right after the vulnerability has been made known to them, when the fewest systems have been patched. So CVE, you probably have heard this term in this conference a ton of times already, but basically it stands for Common Vulnerabilities and Exposure System. It's basically the way that the US government is cataloging the vulnerabilities in software. It's run by the MITRE Corporation on behalf of the US government, and basically each vulnerability has a unique identifier. And they've got this thing called the National Vulnerabilities Database, which contains information about vulnerabilities. It contains like information about the impact, like what components are affected, what the severity is, how to fix them. There's an open source alternative, VulDB. In order for something to be declared a CVE, there is a set of criteria. It's got to be independently fixable. So you can patch the vulnerability without introducing other behavior. It's either acknowledged by the vendor or documented. It affects one code base. So like if it's a library, it only gets one CVE if there's no way to use the library without being vulnerable. And you get a severity score, 1 to 10. 1 is like not a big deal at all. 10 is an incredibly big deal, critical vulnerability. And what we've learned over at Eclipse Adoptium from the OJVG is that the severity score also kind of depends on how you're using that software, right? If a library has a vulnerability kind of in one behavior or a vulnerability that can be exploited in a certain way, if you're using that library in a way that kind of doesn't surface that exploit, then you might have a lower severity due to that vulnerability than other users. So severity has to be looked at in context. So this is like the NVD example. So from the National Vulnerabilities Database for Log4Shell, right? So the infamous one that we've probably all heard of. As you could see, the score is 10 out of 10 critical. It contains some information, description, log4j version numbers that are affected. It tells you a little bit about how it can be exploited, right? It talks about that LDAP and JNDI endpoints issue, and it also contains references to external articles that people have written about how to deal with this vulnerability. So that's kind of what you get with NVD. Beyond the NVD, here's kind of a list of important industry players you probably have already heard of. OpenSSF, this is part of the Linux Foundation. They established the SLSA standard. I think Stuart's got to talk about this tomorrow, about how Adoptium is achieving SLSA level 3, right? I believe there are 4 levels. And with Adoptium, we're working to make your JDK as secure as possible, and this means working our way up the SLSA levels. And they provide the OpenSSF scorecard. The other really, really big name you should know is OWASP, the Open Worldwide Application Security Project. They're the people behind CycloneDX, right? So if you've heard of a software bill of materials, great. If not, it's like in the next slide. They're the people that have established that standard for SBOMs, and they've also provided a bunch of tooling around it, including dependency track, which enables you to take an SBOM and generate things like vulnerability disclosure reports. Think that dependency track, which is a fully open source tool, also has a cache of the NVD in it. So OWASP is really one of the organizations that's helping us understand what's in our software and how it makes it vulnerable. Of course, a lot of open source projects, Adoptium included, live on GitHub. Large host of open source software. GitHub's got a bunch of great built-in tools like Dependabot that will analyze your code. It only does the current version of your branch, and it'll basically try to help you keep your project secure by updating your dependencies, pointing out when there's critical vulnerabilities. There are alternatives to Dependabot like Renovate, but GitHub and GitLab are kind of these big, they're very important because they host a lot of our open source software, and especially in GitHub's case, provide a lot of the infrastructure we might use for things like CI with GitHub Actions. And of course, NIST, the National Institute of Science and Technology, it shepherds the United States' CVE efforts, including that NVD, which is one of the current primary sources of truth for vulnerability information. So we've established that our software can be vulnerable. What do we need to do? First of all, we need to understand what goes into our software. So our software's dependencies and dependencies of those dependencies are all things that can be vulnerable. The way that we describe what's in our software is by using the PURL format. There was a great talk again yesterday morning by one of the people driving the PURL standard. So it's kind of a way to point to, for example, if your dependency is in Maven Central, PURL says it's a Maven Central dependency, and then it'll talk about the coordinates, including the package ID, the artifact ID, and the version. And when a vulnerability is reported, we need to figure out what the impact is and what components need to be patched. And in order to understand what's in our software, we also want to use a reliable SBOM production mechanism. There's more on this on the next slide. The second thing is, remember, the supply chain is not only the components you build in, but also how you build your software. Another important thing is to automate the build, because manual builds are another vector that can be leveraged to deploy vulnerable code, because somebody doing things manually can inject a step you didn't know about. And another key is reproducible and automated builds. So if your build is reproducible, this means that post-fact you can rerun that build pipeline, make sure the version matches by checking checksums, for example, and then try to understand where the problem was introduced. And finally, from the human perspective, you want to understand what's being checked in. Don't check in binaries, right? That's a bad idea, right? The XZ example is a great example of why that's a bad idea. It's very hard for a human to code review a binary. At least you'd have to be a lot smarter than I am to code review a binary. So don't do that. And then keep pull requests short and readable. It's a lot easier to sneak stuff in if you've got like thousands and thousands of lines of code in a pull request, because it's very hard for a human to go through and understand all of that in a timely manner. And of course, I forgot to mention on this slide, but it's very important that your pull requests are reviewed, right? Because the more people there are that are making sure that the pull requests are doing what they say they do, the less likely it is that somebody is going to sneak something in that introduces a vulnerability. So SBOMs. SBOMs are software bill of materials. They're all the libraries you use in the libraries that they use. I like to liken these to the list of ingredients of your software, right? So in the same way that when you purchase a cake, you know that that cake will contain flour, it'll contain eggs, it'll contain sugar, it might contain some fruits, right? The software bill of materials says this library you're using contains all these other libraries. It holds information as well about how the software was built, what OS, what Java version, for example. The SBOM standard is the CycloneDX one. They have convenient Python libraries for building and parsing the SBOMs. SBOMs are machine readable, so usually the CycloneDX ones can be exported in JSON and XML. And they have a Maven plugin and a Gradle plugin to generate SBOMs for Java projects. So it's, I've tested the Maven one, it works really well. You just put the plugin in, and as a part of like your Maven clean install or clean package, you also get your SBOM in the build directory. So it's quite easy and convenient to make an SBOM for a Java project. Just use a plugin. There's also the concept of guest SBOM. So SBOMs are, build time SBOMs are created at build time and will have all the information you need and are generally complete, right? Because if you understand the build process, you understand all the libraries being pulled in. If there's like the shade plugin there, you can understand what happened before it was applied. So highly, highly recommend building your SBOM at build time. CycloneDX, again, great plugins for this. But there's also the idea of a guest SBOM. So a guest SBOM is if you're given a final artifact, say a jar, and for those that didn't know, a jar is simply a, I believe, gzipped thing, so you can un-gzip it and look at all the class files inside. Basically, there are tools out there, including Sift, which is a popular open source library, which will take your jar and will try to guess what libraries are in there. Generally, these are a little bit less precise and might miss some dependencies as compared to the SBOM you build at build time. And so basically, you can build an SBOM either before/during the build or after you've built software. The recommendation is to do it at build time because it'll contain all the information it needs. Another thing is a provenance attestation, right? So it's a claim that somebody has produced some software. As a developer, right, you might have noticed on GitHub that you can get little verified tokens on your commits if you register your SSH key with GitHub and you tell Git locally to sign your commits. So this kind of guarantees that any commit that is claimed to be by you, the person, is coming from a machine that you've registered with GitHub, right? And it's not some malicious attacker posing to be you, because that would be terrifying if somebody introduced a bug and pretended to be you while doing it. And we want to do the same for software, right? So as a software producer, say the Eclipse Foundation, we want to make sure that software that's claimed to be from Eclipse is verifiably actually from Eclipse. Again, using cryptography. GitHub Actions has built-in support for this, so use your tooling to sign your stuff. Makes it easier. Arguments to the build are captured, so like you want to basically, in your SBOM, in the provenance of your software, you want to declare kind of the entire environment which is required to build that software in a reproducible way. So like, you know, what OS you're on and what Java version, for example, and any flags you pass to the build, right? So all this stuff is good to have because then that means your build is reproducible. And then other things like timestamps and other meta information are also things you can include in that provenance attestation. So a brief one on the SLSA framework, and I think as we saw in a recent other presentation, there's a couple different frameworks out there which aim to help software providers show that their builds and artifacts and libraries are secure. SLSA is four levels: no security, provenance and documentation, assigned provenance, hosted build platform, and then hardened build platform. Adoptium is working on level 3. And I think the Eclipse Foundation is also introducing kind of a framework which has similar levels for project security. So keep a lookout for these. There's definitely a lot of guidance out there, and I think in the coming months it'll probably be consolidated into kind of what the levels of build security are. I believe the Eclipse Foundation framework does try to actually kind of, if you meet a certain level of the Eclipse Foundation framework, they'll tell you what SLSA level and what SSDF level and what basically it'll try to map their levels to other levels and other frameworks, because there are a few of them out there right now. This is just a fun one. So as part of validating identities, you might remember I mentioned in GitHub you can be verified if you register your SSH key. But the question is, how do you make sure that SSH key belongs to an actual human? There are these things called key signing parties where people will go with their printed out keys, and they'll meet face to face. They'll like show each other their passports, and then somebody who's like a trusted member of the community, who's got an SSH key that's verified, will vouch for you and sign your key with their key. And it's kind of this chain of trust where people kind of prove that they are who they are because people that are already kind of trusted to be who they claim to be have verified that they are who they claim to be. In GitHub, for example, the other thing is they've introduced mandatory two-factor authentication, right? So that other people cannot use your GitHub account and introduce malicious stuff claiming you're you. Okay, so let's say the bad thing has happened. Somebody's found a vulnerability in your code. The responsible thing to do is to create a vulnerability disclosure report. There's, of course, a CycloneDX format for this. I believe the competing format also by CycloneDX is VEX. It should be pretty simple to produce both. For example, the dependency track CycloneDX project, given an SBOM, can produce both a VEX and a VDR. These cover vulnerabilities in the core code base as well as the dependencies. I work on one of these for Eclipse Adoptium. So the VDR is kind of, it's more convenient for the end user. So the SBOM, as a software producer, you figure out what are all the components that my software eventually uses? What's the dependency tree? The VDR is from an end user's perspective. You come in and say, you know, like you go to a store and you buy a cake. It's helpful for you to have a list of allergens in that cake, right? This cake might contain nuts. This cake might contain eggs. This cake might contain soybeans, right? As a consumer, you want to know what are all the things that you're exposed to if you're using a product. And the VDR is that for software. It's like, if you're using this version of our product, there are these vulnerabilities, and then here's how you can mitigate them, usually by upgrading to a later version of our product. So VDR is kind of the inverse of the SBOM. It's like, given you have a version of the end software, what are all the problems that you might face? So here's a couple takeaways, including this excellent takeaway pizza, rendered in full 2D. The takeaway number one is building secure software is in everyone's best interest, and it's increasingly mandated by regulations. So you don't want to give your clients bugs or your users. Your users don't want bugs to come from you. So the best thing to do is to build secure software. Secure software means secure code, secure dependencies, a secure running environment, and a secure build and deployment process. It's not just your code, it's the whole ecosystem. Tooling is increasingly becoming available to help us build secure, trusted software. SBOM creation tooling, SBOM analysis tooling, hosted build environments with artifact signing. Upgrading is important, so make sure that you are upgrading on to the latest version of library, because that means that usually if there's a patch, the first thing gets patched is the latest version, and it's much easier to upgrade if you're on the latest version because it means that you don't have to upgrade to a later version with different behaviors in order to bring in a security patch. And thank you so much. Secure Java starts with a secure JDK, and we invite you to find out more about a secure JDK at adoptium.net in the docs about secure software. Thank you very much, and if you have any questions. Questions? If there are no questions, I'll be around all day. Feel free to find me, and enjoy the rest of your afternoon.